Next, we're gonna see another example with breadth-first search. This time, we're gonna search with matrix. And our problem today is finding a way to get from point A to point B on the map. As you can see here, our map is presented by an A by A matrix. Each of the cell location is identified by row and column indexes. So the first number is the row index, and the second number is the column index. For example, if we have 0, 1, that's gonna be row 0 and column 1, which is this cell we have right here. On our map, the cell with the number 1 in it represent a wall that we cannot travel to. An empty cell is a cell that we can travel to. So for example, if we start from 0, 0, we can travel to 0, 1, which is the cell on the right. But we cannot travel to 1, 0, which is the cell below and has the number 1 in it because it's a wall. At any given cell, we can travel to left or right and up or down. We can go in 4 directions, but of course it has to be within the map. So if we are here at 0, 1, we can go left to 0, 0, go right to 0, 2, go down to 1, 1, but we cannot go up because it's out of the map. Now our problem is we are given a map with a layout of setup like this or any other setup. We are also given the starting point, in this case that's gonna be 0, 0, and the target destination, in this case that's gonna be 7, 7, and we are asked to find the sorted path from starting point to the destination. If we notice that traveling from one cell to another take the same effort, that means if this is a graph, the edges are equal. So our problem again is finding the sorted path with equal edges. Then we know for sure that breadth-first search can solve this problem effectively, and that's what we're gonna use. Now if we want to translate this matrix into a graph, we can, and it's very easy. If we start at 0, 0, the node right next to it is 0, 1, which is what we have here. And the second node right next to it is 1, 0, which is what we have here. But 1, 0 has number 1 in it. So actually we cannot travel from 0, 0 to 1, 0. So that's why you can see there's no edge linking 0, 0 to 0, 1. So we can just draw an edge from 0, 0 to 0, 1 and totally ignore 1, 0, the cell that representing a wall that we cannot travel to. Now from 0, 1, which is this cell, 0, 2 and 1, 1 are the cells right next to it, the neighbor cells. So we're gonna draw a connection from 0, 1 to 0, 2 and from 0, 1 to 1, 1. And with that we can keep drawing until we finish the whole matrix. So when drawing this, we actually can totally ignore the cells that had number 1 in it, the cell that represent a wall and we cannot travel to. And that's gonna be the graph presentation of this matrix. And we're gonna use Q data structure to implement our breadth-first search, as we normally do. But actually in real life, we already know all of the cells indexes. So drawing this graph is really unnecessary. We can use it, but we don't have to. And you will see that in our implementation later, we're gonna use our matrix here directly without having to translate it into adjacency list or adjacency matrix. Now again, imagine with breadth-first search, if we start here with all possible paths, I'm drawing only 2 paths in red and blue, but we actually have more paths with all possible paths. The first path that reaches 7, 7, our destination, is the sorted path. Why? Because every single path, we take the same number of moves through equal edges to look for 7, 7. And the first one that reaches 7, 7, with that same number of moves, has to be the sorted one. And that's what we're gonna see in here. The blue path that we have takes 13 moves to get to the destination cell, whereas the red path with 13 moves, this can only get here and it needs 2 more moves. So always remember, if our graph has equal edges, the first path that reaches the destination is the sorted path. So for this kind of problem, we already know how to do breadth-first search in the simplest form. Now the additional part that we need to code in this problem is when traveling by layer, we're gonna record all the possible paths and checking if that path had reached 7, 7, our destination. And that's what we're gonna focus on in this problem. Next, let's have a look at our implementation for sorted path problem on matrix. Our breadth-first search gonna take in a map, a starting point, and an end point. And we're gonna output a sorted path to get from start to end. First, we're gonna print out the map. We have a helper function matrix print to help to print out the map beautifully here. So this is our starting point, 0, 0, and this is our destination point with a star here, and that's gonna be 7, 7. That's what we did here. We create a queue and initialize it with the start starting point. We create a set of empty cells that we have seen. We create an array of paths. And we start with the first path, which is our starting point 0, 0. And we're gonna have many possible paths. So that's why it's an array. Then we're gonna start our while loop when we still have new cells in the loop. First, we're gonna dequeue to get the row and the column of the current node. Then we print it out. That's what we have here. Our initial queue has 0, 0. And after dequeuing, the current node indexes is 0, 0. We also create a string of row column index, which is gonna look like this, 0, 0 string, to use in our scene set. So if we have never seen this node before, we're gonna process it. Otherwise, we're gonna ignore it. Now we add the node to our scene list. We create a temporary paths to record new possible paths. We also create a new set of new neighbor paths to keep track of the paths that we have no new neighbor. Now with our current node, we're gonna know the indexes of 4 neighbors, left, right, up, down. We're gonna list them out and put them in here, neighbor indexes. So if we start here at 0, 0, our neighbors are gonna be 0, 1 and 1, 0. The left and up neighbors are out of the map, so we're not gonna consider them. This line is to check if the neighbors are in the map. If the neighbor is a wall, we're not gonna consider them neither. And one more condition is we have never seen this neighbor before. So that means if we start here, we're not gonna consider this neighbor and we only consider this neighbor. And then we're gonna process this neighbor. We're gonna enqueue this neighbor, update the path with this neighbor. So our path is 0, 0, which is from here. Now we're gonna update it as 0, 0 and 0, 1. And we're gonna save that path into the temp path. If we happen to see 7, 7 in the neighbor, we're gonna print the map out. We're gonna return the path and exit the program because we have found our destination. This logic here to make sure we only save 2 temporary paths once with the path that has no new neighbor. It sounds a little bit confusing, but as you're gonna redo this example, you're gonna be able to understand why we need this part. After finish processing the neighbors, we're gonna update the paths. And this logic here is just to print out all possible paths, which we're gonna see later. Now let's play around with our result. So if our map layout is gonna look like this, and our starting point is 0, 0, and our target point is 7, 7. If we run our algorithm, our result is gonna be this path that we see here. The path with the start we see here. And this is the list of the number of steps or cells that we're gonna travel through for our sorted path. Now we can play around with it and modify our map. Let's say that we're gonna block the path here. That means we're gonna put a wall at this cell 5, 6 like this. Now 5, 6 is now a wall and we can no longer travel through. So our new sorted path is gonna be this one, which is the red line that we will see here. Now let's be more tricky and block this one to see what's the new sorted path. So we're gonna block 4, 0 and put a wall in there like this. And our path is gonna go around this wall and reach our destination. And this is the sorted path. And in fact, it's also the only possible path from start to destination. Now let's return the map to our original setting. And let's take a step back and think about how breadth-first search solved this problem. So when we change our map by adding the wall here and here to block some cells, our algorithm produces the new sorted path for that kind of setting. And some of you might think that is because the algorithm is smart enough to adapt to new maps. And that is not true. That's a misconception that is very wrong. Because the way that breadth-first search solved this problem is, it simply starts to find all possible paths. Like the picture that we have here. We have more, but I'm drawing only 2. So breadth-first search simply finds all possible paths. And as soon as it sees a path that reaches the final destination, it returns that path. And that's what we program it to do. So the point I'm trying to make here is there is no magic in algorithm. In this particular case, it's breadth-first search algorithm. It simply just finds all possible paths to go from 0, 0 to 7, 7 and return the first path that reaches 7, 7. To demonstrate that idea, let's just comment out this part where the program stops when it sees the first path and uncomment this logic where it's gonna print out all possible paths. So you can see this is a possible path with 13 moves. This is also another possible path, but it's stuck here. It cannot move no longer. This is another possible path, but it's stuck here, and so on. And you can see that our program actually returned this one, the first path that reaches the destination. Next, let's quickly summarize how to think and solve problem with breadth-first search. First, we build a graph and a nodes data from given data. If the problem is finding the sorted path with equal edge weight, breadth-first search gonna guarantee the best result with the best performance. If the problem is not sorted path, we can examine the data with breadth-first search pattern. That means level by level, like an onion ring, to see if it solves your problem. Next, let's summarize our breadth-first search algorithm. Whenever you have to find some truth in your data, and the truth that you want to know is finding the sorted path with equal edge weight, or you need to visit nodes layer by layer, and the input is graph or matrix, we can use breadth-first search to have a good time complexity of O of n, with n is the number of total nodes. That is all for today's tutorial. Thank you for watching, and I will see you in the next video.